So we've dealt with in many ways kind of the temperature responses, and you can understand why people now might do kind of, you know, a more conventional cardiovascular warm-up, but it doesn't really necessarily explain what is going on physiologically. You can see the thermoregulatory responses, and you can see kind of the way that they can be attributed to muscle function, metabolic reactions, and substrate turnover. But let's delve into this a little bit more by understanding what happens at the onset of exercise, which is called the prior priming effect. So we're going to take this paragraph here, which is a fairly recent paper, and it's really useful to set this up in terms of where we want to go. In 1996, it was demonstrated that pulmonary oxygen uptake, VO2 kinetics, was speeded when heavy intensity exercise was preceded by a prior bout of heavy intensity warm-up. This phenomenon was termed the priming effect. Since this seminal paper, the physiological mechanisms underpinning the effect of priming on subsequent VO2 kinetics has received considerable research attention, not least because of the ability of priming to enhance subsequent endurance exercise performance. This sounds really positive, doesn't it? Because what they're saying to us is that if we do a particular kind of exercise prior to the actual exercise bout that we want to do, they're actually saying that you get an enhanced performance. So is it because we've got speeding of metabolic reactions? Is it because we've got reduction in the resistance of the joint to force generation? Is it because we've got increased substrate availability? Well, in part it's some of those, but not all of those. And we'll explain how this kind of fits into this notion of O2 kinetics. So here you've got on the right-hand panel, the left-hand panel in panel A. And what you've got is you've got time on the x-axis and you've got VO2 in litres per minute on the y-axis. Just focus at the moment on the more solid line. And so what you have is we have a period here which is a 1 minute period where they're at rest, and then we immediately apply the resistance. And so now what happens is there are three components to this response. There is this what we call a phase 1 response here, then we get this cardiodynamic response here, and then we get steady state. This first response here, this first little rise, simply actually reflects, it's the phase 1 response, simply reflects the arrival back at the lung of carbon dioxide, so triggering a ventilatory response. This second phase, though, is the bit that's important, because what happens is at the onset of exercise, the ATP turnover rate accelerates immediately. It's an instantaneous response. But you can see that the VO2 kinetics do not rise instantaneously. It takes, in this example here, anything in the region of around about 2 to 3 minutes to start to reach steady state. Well, if that's the case, and we haven't got a supply of oxygen meeting demand, where's the energy coming from? Well, it's coming from non-aerobic sources, anaerobic metabolism. And so what you have then is this oxygen deficit at the onset of exercise. And what the proponents of prior priming exercise are interested in is reducing the size of the deficit. So here what they've done, they've done bout 1, and they've done bout 1 in what is called the heavy intensity exercise domain. And what they've done is in the heavy exercise domain, that's beyond the lactate turn point of gas exchange threshold, or below critical speed, critical power, or maximal lactate steady state. And they've allowed the participants then to have a subsequent about 6 to 8 minute recovery, and then they repeat that exercise in the heavy exercise domain. And what you see is, here's trial 2, now look at the difference. They reach steady state far quicker, so they have faster what's called fundamental gain in terms of the VO2 response. The actual steady state hasn't really changed, but the time taken to reach steady state has significantly reduced. They've got a tau going from about 30 seconds to a tower of about 20 seconds. But what that suggests to us, if we're reaching steady state quicker, we're reducing the anaerobic contribution, we're reducing the size of the O2 deficit. In this example here, what you can see here is the same equivalent, but it's not necessarily as significant. So they're kind of suggesting there's no effect on the VO2 kinetics in this example here. And what we recognize now is if you do exercise in the moderate domain and then follow it with a block of exercise in the moderate domain, there is no change in the speeding the VO2 kinetics. If you do exercise in the moderate domain, warm up, and then do exercise in the heavy domain, no speeding the VO2 kinetics. Same if you do exercise in the moderate domain and do subsequent bout in the severe domain. There is no speeding of the VO2 kinetics. You don't reach steady state more quickly. However, if you do exercise in the heavy domain and then follow it with a concurrent piece of exercise in the moderate domain, there is some effect, small, but some effect on the VO2 kinetics. But if you do heavy followed by heavy, then there is a very significant speeding of the VO2 kinetics. And even if you do a heavy prior prime, that's kind of a heavy warm-up, and follow that with exercise in the severe domain, there's also significant evidence of a faster VO2 kinetic response. In other words, you get to steady state quicker. Well, how does that translate then to kind of performance? Well, this is data taken from Koga's group, and what they've done here is they've got mean responses, and this is in oxygen consumption, 3rd and 6th minute of heavy exercise. And what you've got is normal muscle temperature and increased muscle temperature. So this is the increased muscle temperature here. So when they've increased the muscle temperature, we'll explain why that's important in a moment. It connects to what we've been referring to. Look at what's happened. They've got a reduced oxygen cost for the same point in time doing constant load exercise. Well, fundamentally what they've done is they've put the participant into the heavy exercise domain. If you're in the heavy exercise domain, there's a greater metabolic cost of doing work. And it sounds counterintuitive because it sounds crazy. Well, how can doing bouts of exercise, which is quite demanding, actually be beneficial? Surely, in the back of your mind you're thinking, well, surely that's creating a fatigue-like state. And this is where you have to recognise there is a playoff, which is kind of what we were alluding to in earlier slides, which is there's a playoff between what is kind of performance and what is physiological. And this is the important part. If I do the warm-up in the heavy domain, yes, there will be a fatiguing effect. But if I allow the participant to recover, and it's not a long recovery, we'll talk about it in a moment, but you're in the region of about 6 to 10 minutes before they do the actual criterion bout of exercise. Although there has been a fatigue, some of that will start to dissipate in the recovery, but we see these faster VO2 kinetics. And what the evidence shows us is, if you do exercise in the moderate domain, although you haven't created the fatigue, and you think, well, that's beneficial, actually the net result is that the balance between the amount of fatigue and the attainment of the steady state plays in the favour of doing exercise in the heavy domain, that the fatigue effect is outweighed by the speeding of the VO2 kinetics, whereas in the moderate domain, the speeding of the VO2 kinetics, because it hasn't occurred, actually the fatigue becomes the problematic factor. So it becomes a really important playoff between the two, and recognising, as we learnt earlier on, that if you get an increase in hydrogen ion concentration, for example, it causes vasodilation. It's beneficial. If you get an increase in potassium concentration, it's potentially quite beneficial. So the assumption that kind of physical exercise or physical activity drives up a fatigue, which it does, but that is negative, we've got to get beyond that and understand how much do I lose in one but gain in the other. And you can see this here. This is a really nice paper by Palmer's group. It came out a while ago now. What they've had people doing is 4,000 metre time trialling. These are quite experienced cyclists. And what they've got is they did a control warm-up and then they did a prior heavy warm-up. And look at the net effect on the sustained power output over the 4,000 metre time trial, all aside from the first 400 metres, the power output, the average power output at each of these time points is higher when they've done a prior bout of heavy intensity exercise subsequent to preceding, the criterion bout of exercise that they've got here. And again, it's fundamentally about accelerating the VO2 kinetics. If it's taking me longer to reach steady state, I'm borrowing more anaerobic energy. If I'm borrowing more anaerobic energy, it costs me, one, it's created a fatigue, and two, I've got less of the anaerobic capacity left. And when we're doing high intensity exercise, having availability from the anaerobic capacity becomes so fundamentally important. It allows us to accelerate. It allows us to perform multiple sprint-based activities. It allows us to tap into that additional reserve of energy. But if we've borrowed a lot of that energy in the warm-up phase, then we've got less of this capacity to work anaerobically.